All right. Good morning, everyone, and welcome back. So before we start today, any questions about the assignment? Just open my chat window here. Just a quick comment. I saw some posts on the forum. That's great, as usual. Just some comments. And you saw also the email that Rancy sent about if you need help, just ask for help, right? Don't underestimate the assignment, especially working with NetCDF can be a little bit tricky. So I wouldn't recommend at all starting, the assignment too late. NetCDF is a great library, but as with many libraries, you need to be used to the language, the terminology, the concepts, and it can be complicated. The assignment in particular is asking you to do something that we didn't show specifically in the lecture. So you will need to look at some examples. Francis also posted a nice example that will help with that. But as I say, yeah, don't leave it for the last minute, okay? All right. Looks like you guys are in very good shape. Maybe Francis, we should start cranking up the level of the assignments. It looks like no one has questions or something. I'm just kidding. We won't do that. All right, let's go to the lecture then. So today we are going to be talking about, and let me know, I'm starting to share my slides. So let me know if you guys cannot see them. You should be seeing them by now. So today we're going to be talking about another tool that, as with many that we have already presented and discussed, are not necessarily tied to C or C++ of this course at all, right? It's a very general tool. What we're going to be talking about is profiling. For some reason, my slides are frozen. Hopefully you guys, there we go. Sorry about that. So we're going to be talking about profiling. We're going to be talking about the different ways in which we can profile code and some of the tools that you can use, okay? But as I say, the concepts, the ideas, the tools, the techniques are way beyond what is C or C++. Of course, some of them are more targeted to a particular language or better suited for a particular type of programming language, like compiled language. But the concepts and the ideas and in particular the goals of profiling and the aims of profiling are generic enough that you can use for any code, for any program that you have running. So what is the main idea? Well, profiling in a very technical way, you can think of a form of dynamic program analysis. It's a very fancy word or phrase to say that you can measure, for example, the space, meaning the memory, or time complexity of a program, given a set of instructions, or the frequency and duration of function calls. Well, what I'm trying to say in a very, very concrete manner is, okay, it's a way to measure how the code runs, how long it takes to run, how much memory it is using, how much resources it is using, depending on what resource you are looking at. And we usually refer to that as the metric. What metric are you looking at? Are you looking at the runtime metric? Are you looking at the utilization of the CPU? If it is a program that runs on GPU, are you looking at the utilization of the GPU, the memory bandwidth? If it is a program that has a lot of communication, we're going to see that in the last part of the course. Is a program that it has a very intense pattern or not of communication. You can look at the I/O, as we discussed last class, or last week, I should say, is a program that it saves a lot of information in hard drive, so that may be the bottleneck of that program, right? So we're going to see also another tool. This will be after the reading weeks, and will be debuggers. And debuggers are used to find bugs in your programs. So we're going to talk about them, but in a similar manner to how debuggers work, profilers are evidence-based methods that can find performance problems. the idea, the goal is that we can optimize. If we find where our program spends most of the time, and it is worth it, that is a substantial amount of time, then we can focus our attention in optimizing the parts of the program that are slow or that they are consuming too much resources or things like that. The main goal or the reason for profiling is we cannot improve what we don't measure. It wouldn't make any sense to say, okay, this is your code, we give you answer table, go and optimize answer table. And say, what do you mean with optimize? What do you want me to optimize? Do you want me to optimize that the time that it takes to run? Do you want me to optimize how much memory it is using? Do you want me to optimize the size of the files that says to this? Well, all those questions are valid questions, but we cannot, even when we decide what we want to optimize, we cannot start the process of optimization until we have a baseline. And the profiling of the program is what will allow us to draw this baseline. And as usual, please feel free to ask questions if you have any, please. So let me start by showing you a few excuse me, lines of a code, a snippet of a code. In this case, it's a code that solves the motion of a projectile. It doesn't really matter what this code does. It's a C code. But what I want you to focus your attention is in a couple of things that we're going to be discussing. As with many programs, there is a sort of, in this block here, there is a sort of initialization of the values that is going to be using. Initialize different values, initialize the type of output that is going to generate, initialize the boundary conditions for the problem, and then there is the main loop right here. And then the main loop has different questions, different conditionals, and then this is the for loop where all the action happens, okay? Again, you don't need to worry this if you think or you wish, you can think about this as pseudocode, meaning a code that does something, but we don't need the details to understand or look at some things of what the code is doing. There are different routines for saving in different type of files. But the one thing I want to call your attention is this tick and talk calls. And we're going to look at them in a little bit more of detail in a second. But again, coming back to profiling, in this case, we are going to be focusing where in the program is time being spent, meaning where in this code are we going to be spending most of the time. One may have a hunch is that this part is within the for loop, right? Because you have a for loop with a given number of iterations. So it's quite logical to think, okay, well, it's somewhere there, but where in particular? So the main goal or the main message here is, okay, we need to find and focus in the expensive parts of the code. And again, the expensive will be measured depending on the metric that you decide to look at. In this case, could be the time of the code being run, or it can be how many iterations in the code is being run. Another thing that we should focus, and we're going to see this in a more concrete example, is don't spend too much time optimizing parts that don't really matter. The main goal of profiling is finding the bottlenecks of the code that can be optimized. Sometimes there are things that are inherent to the algorithm that you are using that you cannot do much. But the parts that can be optimized and can be found with the profiler, those are the parts that one would like to focus on. So I mentioned this, I think, at the beginning. There are two main approaches for profiling, because as I say, these are evidence-based approaches. We have tracing versus sampling, which is directly related to instrumentation versus instrumentation free. So the idea here is we're going to collect information. Let's take the example of how long it takes to run a program. So for tracing, basically, you can think of starting a watch, a clock, at the moment that the program starts and stopping it when it ends. So in that way, you kind of measure how long it takes. Now, sampling, it's a very statistical concept, if you wish, is, okay, I'm going to ask the computer, okay, are you every certain number of times or every certain number of seconds, I'm going to ask the computer, okay, is this program still running? Is the program still running? Is the program still running? And if it is running, which instruction is it running? Which function is it running? So it's statistical in the sense that you don't follow along the whole period of that the program runs, but you kind of sample every certain amount of times if the program is still running, and if it is running, what function it is running. Now, these are related to the two techniques I mentioned after in the bullet points, instrumenting versus not instrumenting the code. So for tracing, which I give you more granularity on what the code is doing, or at least, let me rephrase that. It tells you more exactly when the code starts to run and finish, for instance, or when a function starts and finishes, how long it took. You need to put some instrumentation. And with instrumentation, I mean this kind of commands or instructions like the tick and the talk. So this tick and talk, what basically does is starts a watch and stops the watch. And as you can imagine, this TT variable, we're going to see how to implement a watch in a second, will measure how long took this piece of the code to run, basically from this if statement until the end of the for loop. So that is instrumentation. The instrumentation-free version is when you use an additional program, usually referred as profilers, but you don't necessarily put anything special in your code. Your code remains as it is, and now the profiler in combination with some features of the operating system will allow you to get information of, okay, how long the program took to run, but also which functions were being run, which lines were the most expensive ones, under the assumptions that the program ran for a good amount of time, meaning that the sampling, the statistical sampling that was collected is meaningful, is representative of the overall behavior of the program. All right. Again, let me know if there are any questions. So far, I haven't said anything crazy. Good question, Beran. So the TT in the example means it's just a variable. One way to measure that is using the current time of the variable and then subtract, when you do the talk, subtract the current time. We're going to see we do something like that. I'm going to show you a special or particular implementation of the TikTok routines. So these are not, unless that you use a particular library, these are not predefined functions. You will need to come with your own definition. And as you can see, we are passing them by reference because we need to access them and update, so we can do the subtraction, and then the TT will give you the actual time that happened between these two calls, the tick and the talk. Okay, but bear that question in mind, and we will come back to that for sure. So let me start by telling you a little bit that, and this is mostly thinking about Linux, there are already some tools in the operating system that will help you to measure different metrics of performance. Time is a command that allows you to basically measure how long a program takes to run. So you run time, the name of the program, and voila, you get the wall time that is usually referred to how long it took to run, and the run time, and things like that. Other commands that are very useful, and these are all accessible on the Teach cluster and in most Linux operating systems, is stop, PS, htop is a very nice, I think I have shown some of you maybe, htop is a very nice text-based interface to top. It shows you how much of the processors are being used, the memory consumption, things like that. Then we have things like bnstat or free for accessing the memory records. And then there are even lsof and iostat for accessing input file operations. And then these other ones, tcdump, iptraf, and iftop, are more related to network communication. So again, think about when we're going to be doing just in advance or mentioning something in advance, MPI, message passes interface, when we have programs running in different nodes on the cluster, then a substantial amount of time may be used for communicating information between these nodes, these programs running in different nodes. So measuring that can be also important in those cases. So let me show you a very quick example of how to use some of these commands, which are very simple but quite powerful in the sense that it can give you an overall view of the performance of the program. So one of the simplest ones, and many people use it, is the time command. And the way it works is you write time, and then you execute the program with all the flags that you need. You get the output of your program, and at the end, you get these 3 lines, real, user, and sys. And these are measures of time. The real time is the actual elapsed hold time, meaning for how long the program was running. The user time is the actual user time, meaning that the operating system will differentiate when your program is running versus when your program calls a low-level function, for instance, to save a file or check if the file exists. Remember what we talked last week about file input-output operations? Any of those are considered system calls. So this allows you to discriminate between the actual time that your program was running versus the offload of some operations to the operating system. Now, in addition, or related to that is also the sys time. That is what is called system time. And this refers mostly to input-output operations. So disk access, input-output, those kind of things. And again, this is already a very good information to keep in mind, because now we can start to see, for instance, if your code is mostly driven by computation, meaning using the actual time, or driven by system calls. And in this case, system call will refer to file input operation. So just by looking at this, you can have an idea that about, well, is this what we call a compute-bound program, meaning that most of the time is being spent in computation of any kind, or file input-output operations bound program. And again, this give you very, very concrete insights about, okay, where should I spend looking at in the code? Should I be focusing, minimizing the time that the code is running file I/O, because we know that's the slowest part of any computation, of any program running, or should we focus on the computation part? As you can see, the elapsed time should be the user plus the system time. This is true for a serial program, meaning one instance of the program running. If you had a program that runs in parallel, then this is a little bit more tricky, because in the parallel case, ideally, the user time will be the number of processors or number of threads that you have in your program times the real time. One of the nice things with this information is that one can run testing to identify performance regressions on this. So you can think, okay, if I increase the size of my problem, how this will work, or measure that, and then try to see what is the scale up of these things. Again, we're going to come back to these points when we start talking about high performance computing, how to improve the performance of our code by using parallelism. But at this point, it's more about gathering information about how our program runs, and in this case in particular with the metric of time in mind. This is the other command I mentioned top, super useful. In this case, it's a program. We're looking at a program from a user that is running 8 instances. These are threads. And this tell you how much of the CPU is using. It can tell you how much of the memory is using. It can tell you for how long it has been using. But it also gives you an overall view of the resources being used in that computer. So it's again, top or HTOP, I will strongly recommend to take a look, get familiar with the information being displayed. There is something that when we run our codes, we should keep an eye on it, okay? What else? So those are some tools that, as I say, they are for sure installed in your systems, free to use, ready and available to use. But what happens if we want to, and let me think this. So let me say this, when we use these tools, what we get is an overall picture of what is going on with the program. What happens if we need a more concrete, a more detailed picture of how the program is behaving? Well, at that point is when we're probably going to be thinking about instrumenting, adding these instructions to our code, so we can get more insights about, okay, how this routine, how this function is performing within this function, where it's being spent most of the time, and so on. So let's start by looking at the instrumentation approach. It's simple, but it's quite powerful. It runs, of course, every time that you run your code, and can very quickly identify changes, meaning what made things better or worse. And this is the example of the routines. There are different ways you can define this, but this is the example of the routine that I was showing you in the TikTok functions before. So basically, tick is of type void. It receives a particular structure that we're going to see how is it defined. and basically get the time of the day. That's all what it does. So receives a pointer to a variable, updates it with the actual time of the day when tick is called, and that is it. Okay, it doesn't return anything. Talk, on the other hand, will return a double and basically receive the same type of variable. It gets the time of the day, and then they perform the subtraction, and it returns the value millisecond. That's why you see this conversion there. Okay, so nothing too profound about it. I basically request what is the time of the system at the moment of calling tick, store that, or return that in my t variable. When I call talk, I basically get the time of the system again, subtract those 2 times, and then divide by the factor that gives me the values in milliseconds. That's all what it does. As I said, nothing too profound. What you will need for that, well, you will need to include systime.h, so you get the time of the day function available. Again, depending on what libraries you use, you may get different ones. I believe Boost has a different implementation that you can use, and probably STL as well. Okay, but as I say, you can use this one. You can, if you even Google, there are different ways different implementations that you can use for tick and talk. How it runs? Well, as you saw in the previous example, you call tick for initializing your watch. You do whatever you need to do, and then you call talk. So, for instance, these tick and talk routines basically surround an initialization part. You can surround a big computation part, including a for loop. You can surround I/O part and put as many timers as you wish. At the end, you report those timers. Of course, if you don't report it, they are basically lost. They are just internal variables that don't get accessed by anything else. So you can do at the end a summary. And as you can see, this is C code for the printf, but you can do the C out without no problem, formatted in a particular way, but that's it. In this case, I'm printing the initialization time, the computation time, and the I/O time, because I have these chunks in this pseudo code that I'm showing you. Okay, again, super simple to implement, nothing too profound about it, but it can give you insights very quickly about how the code works. So let me show you an example. Again, it's a snippet of a code. Don't get too much caught into details. Of course, ask questions if something is not clear. But this code, what only thing that it does is a matrix vector multiplication. You will never do this, of course, but you're going to see why you never will do this next week. No, sorry, not next week, but week after the, or 2 weeks after the reading week. So in this case, what this code is going to do is it's going to initialize a vector. So it's initializing x in this case and y. And then it's going to initialize a matrix. And that's it. So I'm going to start my clock here, and then do the talk here. Okay. This is where the multiplication is being done. And there is a flag called transpose in this case, in this program, that allow you to do either the initialization or the multiplication using the transpose of the matrix. Don't worry about this red or purple code. That's something we're going to see. Rances is going to be talking about OpenMP later in the course, but it's a way to parallelize, to optimize this. We don't really care about this, actually. This belongs to these for loops. And all what we are doing here is ticking and talking the computation part. So where the multiplication is happening. We're going to dive into this a little bit, but right now it's just 2 nested for loops that basically allow you to multiply the matrix by the vector x. So one way or another, just to let you know, the only difference between these two are related to where we use the transpose of the matrix or not. And the only thing that changes in the code is the order of the for loops. Meaning, in this case, I'm looping first by the first index of the matrix. In the other case, I'm looping by the second index of the matrix first. Okay? And that's basically it. No much more complication than that. It's just a simple code that does a matrix vector multiplication. Okay? The only thing we did is we just time the initialization part, we time the computation part, and I believe there's an I/O part. I'm not showing that part. It's similar to any IO part that we have seen before, or even in the previous example. So we're going to time that part as well. So if we do that, now in this case, the code is called MBM, matrix vector multiplication. You can pass a flag into the code saying what size is the matrix. So in this case, 2500 elements. And basically, the time in summary, what it tells you is how much time it was spent on the initialization, how much time was spent on the computation, and how much time was spent on the I/O. So the goal of this example is just to show you that by instrumenting the code with the simple tick and talk routines, now you have a very clear view of where the time is being spent. And you can see now that the bottleneck in this code is not the initialization part. Usually that's never the case. It's not the computation part. That is not surprising, but it could be. But it's the I/O part. And you can see not only that, but also the difference order of magnitude in the measurements, right? There is almost a 2 orders of magnitude between each of these different stages of the code. So clearly the computation, as I say, it can be done differently. It should be done differently, but we are not going to be discussing this part today. But the I/O is the clear part where is the bottleneck here. Okay, so this is an example of how one will go about, profiling the code, inspecting which parts of the code are the most expensive ones, the more demanding ones in this case, in the terms of the time. So let's take a quick look at how the I/O is done in this particular code. And there are 2 options for I/O. One is to store the result as text, ASCII text. The other is to use a binary option. Nothing fancy, not an STDF, but just plain binary. So this is how the I/O for the text part looks like. As I say, this is more old C code than C++, but doesn't really matter. So you open the file, you put some headers there, and then you dump the content of the result, and that's basically it. And then you close the file. In the binary, we discussed this last week as well. You just open the file again, and you just dump the content. You allocate the resources and dump the content of the matrix, and that's it. So it's not a bad idea in this case to try to save things and compare things saving in binary. I should clarify that the example I ran before was saving the data in ASCII, in plain text. And in this case, there is something quite obvious, right? When you're going to save this in text, you need to loop over all the elements. We talk about this when we save in text. There is this conversion going on between the number representation that the machine uses and the characters, the strings that are going to be representing those values. So there's a lot of extra operations that are being done when one saves things in ASCII. So there's not really much surprise here to see that could be part of a very expensive operation. What is surprising is that it takes way longer than the computation itself, maybe. Also, you may notice that the code in binary, but this may be an annoyance from the C implementation, is way shorter. So what happens if we try to run this code in binary? Well, I'm going to run, so this is the previous run where we have the ASCII output. This is the second run, MBM, same matrix size, and now I'm going to use the option binary. And you can see the times, they don't necessarily match, right? Because there are variations and fluctuations, but they are quite close for initialization and calculation. But the I/O now is substantially less, right? Is almost a factor of 36 faster if you do the computation. Not only that, if you look at the sizes of the files that were generated, the ASCII file is roughly 90 megabytes, while the binary file is 20 megabytes. So even in terms of size, they are almost 4.5 times smaller using binary. So it's still slow compared to the rest of the code, but now it's at least 1 order of magnitude slower and not 2 order of magnitude. But still, it's something that is easy to see just by instrumenting the code and seeing which part of the codes were the slower in this context. So let me stop here for a second and ask you if there are any questions. looks like no questions. So just a wrap up of this. It's no surprise, as I say, binary formats are way faster than saving data as plain text. There is no conversion either, usually related to smaller files, not necessarily related to performance, but still important. There is no precision loss. And even more advantageous is to use a standardized format like netcdf or HDF5. So this is just a wrap up from our last week lecture on Fire.io. Now let's talk about, so that was an example of instrumenting the code. We strategically added tick and talk routines or functions to different parts of the code, so we can do that to identify very precisely how long each of these parts took to run. Now, the alternative will be to use instrumentation-free approach, and for that we're going to sample the code as long as it runs. So what this allows us to do is to get a finer, even finer grained information about where the time is being spent, because now I don't need to go and, if I really want to do this in the code, I will have to put tick and talks all over the place to see, okay, is the actual operation within the for loop that is being expensive for the calculation, or what part of the IO is being the most demanding one. So instead of, putting 1,000 of tick talks around the code, let's use a different approach. Let's use the sample approach. And the good thing is that there are tools already in place for doing that. So we're going to need the combination of the help of the compilers, because the compiler will add some special instructions in our code that will allow the profiler to actually go and look for those instructions, for those flags, and say, oh, you know what, I was at this moment in time, I was doing this, that kind of thing. So as the program executes, so this is what is going to happen. As the program executes, every so often, the typical time is 100 milliseconds, although this can be configured and changed. And basically, a timer goes off, and the current location of where the instructions are located, or what instruction is being executed, is recorded. So basically, this is related that, again, this is tied to the operating system. The operating system will have a function stack being, okay, it's kind of a pointer telling, okay, which instruction in the code is being executed at this point, and that goes into a particular place store and say, okay, maybe at that time I was executing lines 718, 223, 9, and so on. So the real big caveat with these approaches is that the program has to take a substantial amount of time to run, right? Because think about it's like with any statistical approach, you need to have a good number of samples in order to have a representative result, and this is no different on what that on those means. So you need to have a program that runs for a good amount of time, or maybe increase the frequency at which the samples are collected if it's not the case. But having having the program run for longer time in this case will be of benefit for having more meaningful results and a more complete picture of what is going on. So I think I mentioned this, or if not, we can talk a little bit about this. What advantages it has? It has a very low overhead compared to what you would think is very, very benign. It doesn't affect much of the code. It doesn't require instrumentation. So basically, you won't be modifying your code at all. The disadvantages is it don't tell us why the code was there. So why is you run your code and instead of finding wherever you think it could be the case, you find something else, it won't tell you the story of why the code was spending so much time there. Okay, but it will tell you the code was spending most of this time there. And as I mentioned before, you need to have a good sample size in order to have representative results for your missions, right? So how we implement this? Well, I told you it's a combination of things that we need to tell the profiler and a tool that we will need to use. So I have here an example. This is the example I was talking before, the matrix vector multiplication code. If you are going to use either compiler, Intel, or new compilers, what you need to add are these two new flags. -PG stands for the profiler, so it will turn on the profiler. and that she activates the debugging symbol. So usually what that happens is it makes the results, if you want to look in a debugger, more comprehensive for us, for humans, in the sense that all the binary code can also have the labels of the variables, the name of the variables that we use to define. Otherwise, it will be just hexadecimal code. That's the one that the language the computer actually talks. So we recommend to use these two symbols for compiling when you want to profile the code. If you don't put the -PC, when the profiler runs on your program, it won't do anything because the information won't be passed. So you do need these flags. In the execution, what will happen is nothing much happen in the execution. You run your code as you will run always. You will get an output. And then at the end, if you do an ls, what you will notice is this new file called gmon.out. So basically, that will contain all the information, all these lines of what time, which line, which function stack, which function from the function stack was being called at that given moment in time. Okay, so it's like, again, it's a sampling technique. It's just go and check, okay, what instruction was being executed, what line of the code was being executed, that kind of thing. All right, it's nothing too obscure at all. And if you look, so for looking at the output, what you will do is you will run this command called gprof. It's a tool, it's the profiler tool indeed. And then you will run you will specify what is the file, the executable that you use, and then the gmon.out file that you were using. So this allows to connect information between the sampling and the code itself. And then it will tell you, for instance, in this case, okay, this is the total time, the cumulative time in seconds, then how many times it was called, and then the name of the function that was being called. So it gives the data by function. Depending on your code, it can be useful or not. And you can see that it also goes to very low levels, also calls to, for instance, even when we didn't do that, call to free or alloc or those kind of things. So it can dive into your functions itself. In a toy problem like this, it may not be too useful, but you can add the -- line option, which allow you to profile by line. So it not only dives by function, but it also gives you the information by line. So the line of the code. So it tells you in which line of the code it was actually being executed. Now this comes back to this comparison between a monolithic code and a modular code. If you have a modular code, you have more information by looking at the function. So that's another reason why modularity is a no-brainer here. Okay, but then that's how you will do. So you will run your gprof in your code with the gmon.out from the run, or you will add the -- line flag if you want the times per line and not only per function. So you can see within the function what lines are being called and how many times if that's the case. Okay, so again, very simple tool to use, very straightforward to do, and a lot of information that can provide us. Okay. Just to show you an example, for instance, this is just a chunk of the output. In this case, looking at the calculation part that we saw before. So with the instrumentation, we look at the big sections: initialization, calculation, and I/O. But now with the profiler itself, we can dive into the calculation itself, and you can see that in the line 82 here, is where the multiplication is happening, and the line 113 is where the I/O is happening. So these appear to be the most demanding ones in terms of running the code. Okay. Any questions about this? Again, the use of the profiler is quite simple. Things that one must remember is to include these compilation flags. Usually what happens is when you create your make file, you will have a new rule for profiling, for instance, and then you run your compilation with the profiler options activated, and then you run your profiler and you get the information that you need to about the code. Just a quick summary of gprof. It's almost everywhere. One thing that we have noticed before, this is a disclaimer I had to tell you. sometimes the profiler doesn't work very nicely on Mac OS. I don't know if that's the case. I haven't tried the latest versions of Mac OS with gprof, so that's a word of warning there. It's very easy to script and put in batch jobs, or even in your main file. The overhead is very low, and there are some graphic user interfaces if you really want to try that can give you some hints. I will show you a few ones at the end. But if not, the result that you get is just that list of lines. So it's very easy to follow and digest, I would say. All right. So we have been talking so far, and again, feel free to ask any questions if you have any. I have been quiet today, guys. We have been talking so far about the time as a metric, but what's about memory? In many cases, we see this especially in the supercomputers, right? In many cases, we have users that either come for mainly two reasons, actually three reasons, but I will mention just two. One is, okay, I had to run my program, and it's taking too long to run in my own workstation or even in my own cluster in the lab. So I need a more powerful machine to run this for either longer times or even faster. And the other problem is, okay, my code is crashing because it's starving for memory. I don't have enough memory on my machine. You know, I need to work around that. Well, there are ways that we can mitigate that. We're going to see that again in a couple of weeks. But how can we measure actually these kind of things? What's about the memory utilization? So let's talk a little bit about how to profile memory utilization. So again, that's another metric. And again, there are a couple of tools already. These are not part of the operating system. These are tools from utility programs that you will need to install. This one is an open source, freely available tool. It's called Valgrind. Actually, Valgrind has a bunch of different tools, super useful, super powerful. There is Massive, which is the memory heap profiler. It basically allows you to have pictures of what is going on the memory. You have different ways to run. One way, this is going to be the command that you will run. Valgrind, you select the Massive tool, and then you run in your code. And then for inspecting the output, it's very similar to gprof. You will get a massive.out file, and you will run ms_print. So that will give you an information, a report of basically of the memory utilization. An alternative one is cache grind or cache grind. The tool is cache grind, and then you run the code. And then this is a nice GUI, front end for the cache grind output. And again, take a look at valgrind.org. This again they work straightforward in Linux. I can comment on Mac OS. I don't remember to have used them, but you probably need to download the source code and compile, but they just work out of the box on Linux boxes. Let's take a quick look at an example from our code. One thing I should warn you, though, is that these tools are quite verbose. There is a lot of information going on, and in some cases, it can be a little bit overwhelming. So you need to, first of all, figure out where that information is. This is an output from another code, actually. It's a Navier-Stokes solver. And what it shows here is the time, is the number of iterations, then the time in milliseconds, and then the total memory being used. And then it separates between useful heap and extra heap and stacks. But the important thing is it gives you the information of where in the code the cost to the utilization of the memory is being done. Basically, where are you allocating memory? Where are you grabbing more memory or less memory? And the percentage of memory. Again, it's quite verbose, but sometimes it's important to get familiar with this output and take a look. They have really good documentation as well in the website. But now let me go a little bit back to the interface between the architecture and the software. And let's talk a little bit. I don't remember if we have done this yet on the course. We're going to come back to this and talk a little bit more on detail about this. But let me just start with a quick and light approach to this. So we usually have two types of memory on the computer. So the main memory, or the memory pool, as we like to say, is you know, if you ever open a computer is the chips that you can put the memory and say, okay, what is the total RAM of my computer? So that's the memory. Believe it or not, that memory is slow. Of course, it's not as slow as accessing the hard drives. That is the slowest part, I would say, because there is the mechanical component. But this is still slow compared to the other type of memory, which we call cache or cache lines. So cache lines are small pieces of memory that are located very close on top of the microprocessor. And the way why this is architected is that if the microprocessor will have to go and grab information from the big memory, it will be way slower than what it is. So what the microprocessor does usually is, let's say we have an array, and the green, bluish, and red elements are different chunks of the array. Whenever the processor needs to access elements, let's say the first part of the array, it will go and copy as much memory has in the cache into the cache. So let's say the first line of cache is copied next to the microprocessor. It does the operations, and then it does the other operations and so on. So what happens usually is let's think about this matrix vector multiplication we had before, that example. And let's say, okay, we need to multiply, and there are a few of these cache lines, right? There are a few, and not only that, there are different levels. So you may have heard of cache level 1, 2, or 3. So there are different levels of cache, meaning how close that memory and how fast, in other terms, is that memory for being accessed from the microprocessor. So let's say that we want to perform the multiplication. So the microprocessor goes, grab the first line of the array, puts that there. It may go and grab the first line or elements of the matrix and put there and perform the multiplication. Now, if it happens that, and this is where things start to matter, and you will see this in the code, how we define what we call cache-friendly code or not. If it happens that we are doing an operation where all the elements are continuously written in memory, meaning that the processor grabs this line, let's say 8 elements, and then can operate immediately with the second and the third and fourth and so on, then that is good for the microprocessor because it doesn't need to waste time going and grabbing the second line until it's done with this, right? So it utilizes all the elements in the line and then discard that, grab the other one, and that way it's efficient. Now, the alternative will be that, okay, let's say the array is structured not continuously, but in a different position. So let's say the algorithm or the program grabs the first line, uses the first element, but then because the way it's implemented, instead of continuing with the second, it needs the next one from the next chunk. So basically what happened there is the microprocessor grabs the first line of cache, uses the first element, because the next element that needs is not part of this line of cache, needs to go to the other one, discard that, grab the other one, and so on. And it does that for every element, basically. So this is what we call a cache miss, basically because we are not fully utilizing the information that we load into the cache. This can be as 10 times slower than a performance where you have all the elements being utilized completely aligned, okay? So this is an important thing. And how we can see that in our code? Well, let's go back and take a look at our multiplication algorithm, right? And this is one of the reasons why you never will do this, and you will use libraries that have already implemented this kind of called cache-friendly implementations. So in C, and this is another important thing to consider, this depends a lot on the language that you are using. What in C is a cache-friendly code, in Fortran is quite the opposite. Okay, just to give you an example. So in particular, in C, cache-friendly order is to make the last index most quickly varying. So what it means is, so the first for loop here, remember this transpose flag I told you before? Well, the first index here, so the for loop goes ij, and the way to access the vector or the matrix here is ij, right? So basically we're making the first index vary quicker than the second index, than the last index in the array. In the other for loop implementation, what we did is basically swap the order. So if you make the first for loop, meaning the outer index, varying in the second position, that is basically a cache miss for each iteration that you have. Okay, why is that? Well, it boils down on how to C represents these multidimensional arrays, how they place on the memory. C being a row major representation, it means that it will lay down continuously chunks of memory for rows representing in your matrix. Fortran is a column major representation language. It lays down columns representing your matrices. Okay. At the end of the day, how you allocate and how you position those things, you may have the control, and that's why the transpose flag was there. Again, we are going to come back to this in more details in a couple of lectures, first in how the cache works, but also how the memory is allocated. But why I wanted to mention this is because this will affect the performance, not much the utilization of the memory, because the memory is still the same, right? We're still using the same amount of bytes for representing the blocks of the matrix, but how we lay down the information on the memory will affect the performance in terms of how fast the code is. Now, these things can be visualized with PyGrind. You need to use the cache grind option, and then the KDE tool, kcache grind, and this works for, so the tool works for any operating system, but you need to have the output file and the executable available for visualizing that. And it can show you very quickly. It's something that is easy to determine for the operating system and these tools when you have cache misses. So it's something that is related to the time metric, but also how we lay down things on memory. I hope that it has been clear. This is more or less how the kcache grind tool look like. So you have the different calls. You have when there have been more allocations of memory, and where if there are cache misses, it can tell you that as well. So one thing to notice, and if you compare, remember this transpose flag is activated by -- transpose. If you run that, look at this, the calculation is, this is crazy, the calculation is of the order of the initialization. So you spend as much time computing as initializing your values. But in any case, so the bottom line here is we saw different cases of performance, of profiling different metrics, time and memory utilization, but also we saw an imprint of how we lay down things in memory affecting how long it takes to run something. So that's probably something to bear in mind. It's called cache thrashing or cache misses, as I say. How we define which, these flags with command line arguments. The flags for those, you do what is called parsing of command line arguments. We used to have, what was that, Francis? Assignment 4, I believe? Yeah, I think it's assignment 4. We used to have in assignment 4, one additional point. We took it away this year because we felt it could be too much to us, where all the arguments, or most of the arguments in the answer table, we ask you to pass as flags. So it's just an exercise of it's called parsing. Basically, you grab the command line arguments with RC and RB. You count how many of them are, and then you do some trimming of the strings. So in this case, -- math size equal the value. Then you say, okay, I trim this thing, that's my keyword, and then you identify the value and you get those things. If you Google it, there are tons of examples. It's called argument parsing. We can post some examples in the forum or in the chat if you're interested. It's quite useful, I would say. The way I usually prefer, though, is to use, it depends on the application, right? But the way I usually prefer to deal with that is to pass an argument indicating all these arguments as parameters. It's called a parameter file or ID parameter file, depending on the application again. And the reason why I prefer to do that is because you have some sort of metadata associated in how you run your code. So if I change some parameters, then I can keep a copy of that file or stagger that file in my repository. And then I have the metadata of how I run these things. If I just run this in the command line, well, I need to take note of which were the options I used for running the program, right? But if I had this in a parameter file, then I can keep a copy of that parameter file. It's a small, tiny text file, so it doesn't really matter. And I have the metadata associated with that. Just an idea. Sure, for sure, we can definitely post that. Okay, just let me finish with a few more tools that are there, in particular when you are going to do this in the high performance computing realm. Some of them are free, some of them are proprietary. Scalaska, I believe, is a proprietary one. Open Speed Shop is free. Tau, I believe, is free. I don't remember HPC Toolkit. But Allinea map, which is one of the best ones in the market, is a proprietary one. You actually need to pay for a license. The good news, though, is that we do have licenses on Cynet. The bad news is I never remember if they run on the Teach cluster, so Francis can comment on that. But these ones are super useful because all what we have discussed today, as you can imagine, get a little bit more nasty and complicated when you do parallel implementations. So Allinea map was for profiling, but there is the actual name now is Forge, I believe. It has also a debugger, and we're going to see this in detail. But when we're talking about debugging in parallel, it can get really, really tricky. Intel has its own tools. Those usually are proprietary, but the good news is you can always get a hand of them by using a trial version or a student version. I believe even now, most of the tools, I think I learned this last semester, most of these tools are freely available if you say you're doing this for research and not, a company or something like that. So if you are performing this for your own research, you can get btune, which is the suite that includes all the things. If you are doing things in Mac OS, Xcode is your friend. That's where all these tools, profiling of memory and speed comes. And if you are using GPUs, well, you will need to use the NVIDIA, well, depending, again, let me rephrase that, depending on what GPU type you are using, NVIDIA or AMD, you may need to use NVIDIA Profiler, or I don't remember, maybe Francis recall the name of the AMD tools, but because, there are proprietary things, each GPU has its own set of tools, but the NVIDIA Profiler is quite good. It's called gprof, and it's very, very, very nice tool as well. Yeah, so as I mentioned, the Intel tools are a suite that include performance, memory, in particular because Intel has these special chips that can perform a lot of operations, vectorized operations, has a vector thread advisor and a trace analyzer for parallel implementations. So cool, DDT. So Francis has mentioned DDT should run fine on the Teach. So that is part of the tools that of the Allinea tools. So that's great. And that's how you will do it on Cynet. I don't remember if this is the actual version. I should have checked that. I apologize for that. But we strongly recommend that you look at DDT. We are going to look at DDT in detail when we do the debugging session. But you basically load your compilers and you load the DDT module, and then voila, it just works for you. One of the nice things of the DDT module is that you can use perf report. I think we had this discussion, and I think perf report works. I think. So if it doesn't work, then let us know. The way you will run it is perf report. In this case, it's a MPI code. So you don't necessarily need to run this if you have a parallelized code, an MPI code, and then your application. And the nice thing is it generates reports in either TXT, HTML, or map files. And they are really nice because it's a very comprehensive tool. It tells you even if your code is compute bound, memory bound, communication bound, IO bound. Really, really nice tool. Remember that you need to compile with the -c flag because that is what makes most of the instructions also connected with the name of the symbols of the variables that you give or the functions that you give to your code. This is more or less how a HTML version of the report looks like. It looks very, very professional. It tells you a summary, overall summary of your application. This kind of diagram is an interesting diagram. It is basically telling you if your code is at the bottom of this triangle is compute, MPI means communication, and IO means file input-output operations. So depending where you find yourself in this diagram, you can say, oh, this code is compute-bound. In this case, the example that was run is a compute-bound code. It tells you that. It tells you how much of the time is being used in computing, how much in communication, and almost nothing in IO in this case. That's an ideal code, I would say. But as you can see, and it has tons of other information. You can keep scrolling and more details pop up. Really, really cool tool to look at. Maybe this is a little bit out of scope right now. We will come back to this, but this is how a communication pattern will look. So it gives you as much detail where you can identify where call to functions and information between processes is being sent. So I'm kind of selling you on DDT here, or Forge as it is called. So really cool tool to look at. So one more summary for today. Just a wrap up of everything that we have talked today. Two main approaches to profiling: traces versus sampling. You can put your own timers in the code in and around important stations, find where the time is being more spent, and if something changes, you really quickly know what changed and where. gprof is super easy to use. It's an excellent tool to find where the time is being spent as well, and there is no instrumentation required. This is kind of an advice if you wish. Know where the expensive parts of your code are and spend programming time accordingly. Meaning, if you know the initialization is a very small chunk of the program that is being used, and it's something you have to do because initialization has to be done. Well, compare how much is with respect to the rest of the code. It's something that you may want to spend time optimizing. Probably not. Bygrind is a great tool for all what is memory things, performance, cache, and use. We are going to see Bygrind again when we do debugging, because there is a very nasty bug called memory leak. I think we talked a little bit about this when Rancid was talking about array allocations. If you forget to deallocate your arrays, you're starting to leak memory. And in some cases, that can lead to basically your code crashing because you run out of memory. Allinea map is a great tool if you have it available and you do have it on the cluster. It can also run in a client-server mode, so the GUI that is offered, which can be slow to use through X-Forward, it can be used in a client-server mode, so that's something also really nice to have. And I think that's mostly what I have for you guys today. Let me know if there are any questions. I answer you in a second, Brandon. So just a question about office hours. And by the way, office hours will be tomorrow. I think tomorrow is at 2, right? 2 to 3. Cool. Right. Okay.
Hi.
Yes.
Can I ask a quick question?
Sure, please go ahead.
I'm a bit confused with the assignment. So.
Yeah, sorry. Yeah. Let me pull. Yes. Go ahead. Tell me about. Let me bring the assignment description. You can start to ask your questions.
Yeah, I have finished writing the code for writing text file and the binary file, but I'm confused with how to write the netcdf file.
Okay, have you looked at, let me start by asking, have you looked at the example we posted?
Yes.
Okay.
I first create a netcdf file and then add the dimensions and then add a variable, right?
Okay, yes, that sounds good.
And when I put the variable, my variable name is the ounce var, the ounce variable, ounce var point put var. Use this function to add the data into the netcdf file, but it says that the let me check. It says the terminate called after throwing an instance of netcdf exception that nc bad ID.
Okay.
netcdf not a valid ID. I'm wondering what is how can I solve this problem?
Okay, so we may, so that could happen for a couple of reasons, but what I'm thinking is we may need to see your code to